Hello everybody. We start. Today's lecture 8 of this univariate calculus or analysis course, and section 8.1 is about classes of integrable functions. And please remember that last section, which was called formulation of the equivalence between Darboux integral and Riemann integral, is just only formulation. So I decided to skip the proof because it is rather complicated, and if you want, you can look into Rudin's book. I recommend it, in fact, because I follow mainly these Walter Rudin principles of mathematical analysis. Oops, I'm not sure. Principle of analysis may be poof. I'm not sure in English title, by the way. Sorry. I know Russian translation. I forget to look what is about precise English original title. Sorry. So in Rudin's book, of course, this is not for the first reading, as it is said in the introduction, but nevertheless, I mean, the structure and the sequence of material is very good, and I follow this in my lectures. And your book is ready in some sense. I don't know why Leonid Pankratov didn't download it into. Oh, in fact, maybe it's just some difficulties of technical kind. And I would say concerning integration, the lecture notes by Leonid, they follow mainly another book, Zorich, Mathematical Analysis. And that is slightly different if we are talking about analysis from Rudin's. And so, taking into account what was given last time, namely the Darboux integral and Riemann integral, they are equivalent, right? So it means that we have two different definitions of the integral, and I'll use both of them depending on what is easier to use. That is how it will be in future. So part of proofs will use Darboux definition, part of proofs will use Riemann definition, and depending on what is easier. That is, so I spent some time in explaining two definitions, but as a bonus, we'll choose between two different versions in future. So now it's one example. So classes of integrable functions. Theorem 1. If f is continuous on AB, then f is integrable on AB. So I'll not indicate either Riemann or Darboux because we know it's equivalent, right? So we say just integrable. So integrable, Riemann or Darboux, what is equivalent? What is equivalent? Proof. We know from the first semester that if is continuous on AB implies there was counter theorem about it. Counter theorem. Of course, I don't remember its number, and I don't think it's a good idea to refer to numbers. F is uniformly continuous. On AB. What is uniformly continuous? Uniform continuous. What it means? For arbitrary epsilon greater than 0, there exists delta greater than 0, such that for all x and t from the interval AB with distance less than delta, we have f of x minus f of t less than epsilon. And let us choose the epsilon slightly smaller, like epsilon over 2 times b minus a. Now, let us consider arbitrary partition P of our interval AB such that its norm less than delta. Norm of partition less than delta. So it means that the distance between that means maybe what it means that for arbitrary I from 1 up to n we have xi minus xi minus 1 less than delta. Now, what follows from those two considerations? So, look, we took arbitrary partition. So, we took arbitrary partition of our interval AB such that maximum of the length, it seems this is here, right? From the first glance, it seems maximal of intervals is in the first. That doesn't matter. Maybe that one doesn't matter. So maximum is less than delta. And in particular, it means that every interval, every small interval, has small length, less than delta. Now, let us consider the difference between supremums and infimums, which were used in Darboux sums. Supremum minus infimum. So you see, look, for every value, look, for example, consider one interval, xi minus 1 xi. Take arbitrary value, two values, x and t. What is difference between them? It is for sure less than epsilon over 2 times b minus a. So take arbitrary x and t here. X, let's say t, right? Arbitrary. Then, what it means concerning supremum. What means supremum? It means we can approach this supremum as close as we want, right? So there is for arbitrary, let's say eta greater than 0, there is a point, let's say x, and a point t in our interval xi minus 1 xi, such that f of x belongs to the interval mi minus eta mi, and f of t belongs to the interval from little mi plus eta. That is from definitions of supremum and infimum. And, sorry, that is not from this one, that is from this, follows from the definition of mi and little, capital Mi and little mi. So, Mi is supremum, hence we can approach it as close as we want, right? Then, from this follows that Mi minus little, capital Mi minus little mi, what is it? Less or equal than, I'll write like that, Mi minus eta minus Mi plus eta, that is equal, right? Equal, plus 2 eta. And we know that capital Mi minus eta is less than f of x. And little mi plus eta is greater than f of t, and we have here minus f of t plus 2 eta. So, but we know that this is less than, look, both x and t both x and t, belongs to the interval xi minus 1 xi. And if they belong to one interval, then distance between them is less than delta. Because look, we choose the interval such that the difference between xi and xi minus 1 is less than delta, right? So the distance between x and t is also less than delta, for sure. Because both x and t lie on the same interval. Right? So here distance less than delta, both lie on the same interval, hence the distance also is less than delta. So x minus t less than delta, hence we have here epsilon over 2 times b minus a plus 2 eta. So now look, we start with this number, and this number doesn't depend on x and t, right? Once we choose interval xi minus 1 xi, and we choose the function, both numbers are determined completely, right? They are given, fixed. And we know this fixed number is less than that one for arbitrary eta greater than 0. Hence, we can deduce that mi minus little mi less or equal epsilon over 2 times b minus a, strictly less than epsilon over b minus a. Now, let us consider the difference between upper and lower Darboux sums. I hope I didn't change the order. I don't remember now which order I used. P or F or FP. Can you look? Please look in your lecture notes. I forget about the order in Darboux sums. PF or FP? PF like that? Okay, good. So, what is it? We have the sum capital Mi times delta xi, that is upper sum, minus lower sum, which is Mi delta xi. That is, if we use algebraic transformations, right? So common multiplier delta xi is taken outside brackets. And now you see every bracket less than the same number epsilon over b minus a, right? So I may put epsilon over b minus a times sum delta xi. And this sum, so what it means? We summarize all lengths of small intervals. Altogether they give the length of the whole interval, b minus a, right? So that is precisely epsilon. So what it means, for arbitrary epsilon, we found a partition. In fact, we took arbitrary partition with such norm, right? But for us, it would be sufficient to find just one partition such that the difference between upper sum and lower sum is less than epsilon. Because then by integrability criteria, Darboux integrability, right, follows that f is integrable. So that is maybe number may have a look last lecture. Have you last lecture? Okay. What is number? Darboux integral. Yeah, necessary and sufficient condition for Darboux integrability. That was theorem 1 from 7.2. Theorem 1, 7.2. So f is Darboux integrable, and that is the same as Riemann integral. And it means theorem is proved. Theorem is proved. Next theorem shows another huge class of functions which are integrable. So theorem 2. May I clean the blackboard? No questions? Okay, then I'll clean it. So, theorem 2 if f is monotone on a beam, then f is integrable on AB. So, proof. Without less of generality, without loss of generality, we may suppose f is strictly increasing, let's say. In fact, doesn't matter if strictly, just increasing, is increasing. Analogously, we can consider the case of decreasing function without loss of generality. So, because for decreasing functions the proof is completely analogous. Then, look what it means. It means that f is increasing by definition. If x1 less, okay, x1 is not good, less t less or equal b, then f of x less or equal f of t. So that is increasing function. Then, what is supremum? I mean capital Mi, supremum over interval xi minus 1 xi of our function. If the function is increasing, then supremum is the value at the right end of the interval, right? So that is obviously f of x. And analogously, little mi, which is infimum, is f of xi minus 1. Now, let us consider the difference between upper and lower sum of our function. So, look, what is upper sum? That is sum for I from 1 up to n, mi times delta xi minus sum for I from 1 to n, little I delta xi. Now let's substitute the values. So that one is yeah. F of xi times delta xi minus sum f of xi minus 1 delta xi minus 1. Now let's write down it in more details. So, yeah, f of x1 times x1 minus x0 plus f of x2 times x2 minus x0 plus so on plus f of xn times xn minus x1 here, sorry, xn minus xn minus 1. That is the first sum. Then minus the second sum will be quite analogous, but we have the following. Okay, let me finish it here. Plus f of xn minus 1, xn minus xn minus 1. Yeah? Yeah. Now, let us collect now terms in a different way. Namely, let us collect terms with the same value of our function. So you see f of x0 is in only one place, right? So I'll start with it. Minus f of x0 times what it was, x1 minus x0. Then plus, now what is about f of x1? We have f of x1 times what? F of x1 times x1 we cancel because not cancel. Now I forget to make one very important thing. Look, here I took arbitrary distribution, right? So now let us choose a distribution, partition P, such that all delta xi are equal. So A is x0, x1 is A plus B minus A over n, x2 is A plus 2 times B minus A over n, and so on. Right? So we took equidistant nodes. Then what happens? This is B minus A over n, right? All those differences. And then what will happen? F of x1 will be with multiply B minus A over n minus B minus A over n, right? So they cancel each other. And what remains? So times 0 plus so on f of x n minus 1 times 0 plus f of x n times xn minus 1, what is B minus A over n, in fact. So we have B minus A over n times f of B minus f of A. So we took arbitrary n, natural, consider equidistant points, choose show camera till end of screen. Показать камеру до конца экрана. Загубить. Показать камеру до конца экрана. Что он хочет сказать? Till end of screen. So it seems something was not seen. Okay, so you see, n is arbitrary natural number. What happens if n tends to infinity? Tends to 0, right? So it can be made as small as we want, right? For sufficiently large n. So for arbitrary epsilon greater than 0, there exists n natural such that for all n greater than capital N, we have inequality u of pf minus L of pf less than epsilon, because this number can be made less than epsilon. And it means, once again, of course, partition P is like that, with equidistant nodes. It means that we have, again, by Theorem 1, section 7.2, that f is integrable. Okay. Maybe something was lost on the blackboard, not on the screen. So, now you see, we have two huge classes of functions which are Riemann integrable, right? Continuous and monotone. You can ask, oh, maybe all functions are integrable. The answer is no. And let's start with example 1. It is called Dirichlet function. I think we used it once. It is 1 for x rational, 0 x not rational. So I'll prove that f is not integrable on AB for arbitrary a, b, a less than b. Real, of course, right? Real. Why? Let me erase the proof. Why it is not integrable? Because take arbitrary partition of arbitrary interval. Then for arbitrary I, there exist points x and t on the interval xi minus 1 xi such that f of x equals to 1, f of t equals to 0. Because as we know, on any interval of the real axis, there are both rational and irrational numbers. Hence, capital Mi is 1, little mi is 0. And it means that the difference between upper and lower sums is equal to here we have 1, here we have 0, so b minus a doesn't matter which partition we consider. And it cannot be made as small as we want. So again, by Theorem 1, section 7.2, f is not integrable. Because we cannot find a partition with arbitrarily small difference between upper and lower sum. Let's consider another example, very similar, that is called Riemann function. Of course, essentially more famous is Riemann Zeta function, but that is different story. So f of x equals to 1 over n if x is m over n, mn are mutually simple. And 0 if x is irrational. So we know that every rational number can be represented as a ratio of two integers, right? And we have only one possibility to represent it by mutually simple. Of course, m integer, n is natural, like that, to include negative numbers. And then this function is well-defined function. Okay, let's have a break, right? Okay, let's continue. So now we will prove that f is integrable on AB. How we should proceed here to include, of course. Let me erase former example. So the idea is as follows. Let me draw. Of course, I cannot draw the graph as usually. For the simplicity, consider A0 b equals to 1. That is slightly simpler for considerations. The proof is not differ very much. So look, what we have for 0, of course, what is f of 0? F of 0 is a little bit strange according to this definition, right? So we can represent 0 as 0 is 0 over n for arbitrary n, right? And of course, it makes no sense to talk about mutually simple numbers here, right? So maybe it's better to take by definition 0, 1 over 1, right? Because f at 1 is certainly 1, right? And in fact, the value of our function at arbitrary integer number is 1, obviously, right? For integer number. If x is integer, n is 1, then f is 1, right? But at 0, okay, it's natural also to take f of 0 equals to 0. If you don't like it, then just add one extra value. If x is irrational, oh, here it was irrational, r minus irrational. Either x is not rational or x is 0. So at 0 also 1. Then at 1/2 we have 1/2, right? Then at 1/3 and 2/3, okay, somewhere here, right? 2/3, the value will be 1/3. Then 1/4, and 3/4, it will be 1/4, right? Like here. And so on. So you see that values will be smaller and smaller, right? Even at rational numbers. And values at irrational are always 0, according to the definition. So now the idea is as follows. Look, we want to prove that the difference between upper and lower Darboux sums can be made as small as we want. So we need to construct a suitable partition P. Suitable partition P. How we'll do it? First of all, so we need to find a partition P with this difference smaller than epsilon. That is what we want. How we can realize it? Look, you see, where we have problems. In fact, for arbitrary partition, what can we say about lower Darboux sum? Look, lower Darboux sum, we take sum of little mi times delta xi. Little mi is infimum of values of our function over an interval, right? And doesn't matter how small interval we consider, right? There are irrational numbers on that interval, right? So every interval contains both rational points and irrational points. And value of our function at irrational point is 0, right? So all little mi are equal to 0. Doesn't matter which partition we consider. So lower Darboux sum is 0 for arbitrary partition. But for upper, it's quite different, right? Because, for example, for interval xn minus xn, we have mn equals to, remember, xn is 1, right? So what is supremum of our function on the last interval? 1, for sure, right? It's for sure. Doesn't matter which partition we consider, right? So how can we obtain this inequality? It means that we need to take this interval very, very small, right? So the idea is, look at our graph. We have very few points where our function is large, right? So what we should do? We should take a small neighborhood around each of those points where the function is large. So here, okay, we don't go to the left of 0. There, around 1/2, and so on, right? So we should take small neighborhoods near every point where our function is sufficiently large. Then, in our difference, we split the sum into 2 parts. One of them corresponds to those small, right? Very small intervals. So altogether, they should give very small number. And other part should be small because of values of our functions. They should be small enough. That is the idea. So, how to realize it? Okay, first of all, we have arbitrary epsilon, right? So, there exists natural n such that for all n greater than n, we have 1 over n less than epsilon over 2. So that is what I said about consider large values. So large values are those where little n is less or equal than capital N. And we have only finitely many, right? So there exist finitely many points, let's say Ti rational, such that Ti can be represented as m over n, where m and n are mutually simple, and n is less or equal than capital N. So it's very complicated, in fact, to find precisely what is this number, right? Because you see, for example, with denominator 4, right, we have 2 points, 1 over 4 and 3 over 4, because 1 over 2 was considered before, right? Then 1 over 5, 2 over 5, 3 over 5, 4 over 5, all of them included, right? Then with denominator 6, 1 over 6 is included, 2 over 6 is not, because it was before, right? 3 over 6 again was before, 4 over 6 again was before, only 5 over 6. So it is really difficult to find precisely what is this number. But doesn't matter, finitely many, that's all what we are interested in, right? So then take points xj, j from 1 up to, let's say, m, not m is not good, okay, capital M, such that union of intervals not good, how to say, okay, let me explain what I want. Look, those points Ti, right? T1, okay, T1 is 0, T2 and so on. 1 is T, I don't know how many, doesn't matter, let's say N1. So these are finitely many points. Now what are xj? Xj are around every point. So here we have x1, x2, x3, okay, T3, x4, x5, so on. The very last will be x capital M, right? So yeah, such that rigorously speaking 0x1 contains T1, okay, then maybe I'll write another way. 0x1 together with union for j from 1 up to, let's say, m minus 1, x to j, x to j plus 1, and union, the very last will be 2m minus 1, x to m 1. 2m, let it be. Here 2m, not m, but 2m. So, in fact, the idea is very simple, but it's rather complicated to explain. So once again, look, we have finitely many points t. Points t are such that they have denominators sufficiently small, right? Because then we don't have this inequality. So we have points near each of those ti, right? Okay, it may happen that, for example, here T3 and T4 together, right? But we should take points around all of them in such a way there is only one thing which should be satisfied. Namely, look at this, and what is important, and x1 plus sum from j equals to 1 up to m minus 1 x to j plus 1 minus x to j plus 1 minus x to m should be less than epsilon over 2. So, the sum of lengths of all those intervals should be very small, right? That is the only condition which should be satisfied. And now the partition is constructed. So, P is our partition. Okay, we have 2m plus 1 is 1, right? That is our partition. Why it is suitable? Because look at the difference. U of Pf minus L of Pf. L of Pf is always 0, as we know. So we have only sum j from 1 up to m plus 1, mj delta xj. And we split it into two sums. So j from 1 up to, which should be considered only odd, up to m to j minus 1, and then m plus 1 here, m plus 1 should be here, times delta x to j minus 1 plus remaining. Remaining have even numbers from 1 up to m to j times delta x to j. Then what happens with this odd? Look here. Delta m is supremum of our function. But our function is always less or equal than 1, for sure, right? So, for the first sum, I'll use very rough estimate, just by 1. So less or equal sum j equals to 1 up to m plus 1 delta x to j minus 1 plus, so for the first sum, estimate supremums by 1. For the second sum, we do in a different way. Namely, look what happens here. Capital M to J, what is it? So now, if we take even number, then we consider an interval which doesn't contain points ti with small denominators, right? So all denominators of rational points inside those intervals with even numbers, all denominators of rational points inside those intervals, they have denominator greater than capital M. So it means that values of our function over those intervals will be less than epsilon over 2. So I can write here plus epsilon over 2 times sum j from 1 up to capital M delta x to j. Now look, the first sum was chosen to be less than epsilon over 2, right? From the beginning, we chose all intervals around points t in such a way that the total sum of lengths was less than epsilon over 2, right? So the first term is less than epsilon over 2 by our choice of intervals. And the second, look, here we have sum of all intervals, right? But with even numbers. And that is, of course, less or equal than the length of the whole interval, right? Which is 1. So I replace this sum by 1. So we have epsilon over 2, and there is epsilon. So we constructed a partition such that the difference between upper and lower sum is less than epsilon. Hence, the function is integrable. So you see, two examples, compare them. Right? Seems to be not very different. So for Dirichlet function, you have 1 at every rational point. For Riemann function, 1 over n at every Riemann point, at every rational point. But one of them is not integrable, another is integrable. Right? Okay. Now, I think I'll go back to this a little bit later. And section 8.2 arithmetic operations or properties, main properties of integral. A2 main properties of Riemann integral. Theorem 1 in that section if f, g are integrable on AB, then, okay, that is first property, then f plus g is integrable on AB, and integral of the sum is equal to the sum of integrals. Second property, if f is integrable on AB, then for any real number c, CF is integrable on AB, and integral CF of x dx equals to c times integral f of x dx. 1 and 2 together are called linearity of integral. So these are linearity of integral. Next is monotonicity. Monotonicity. If f, g are integrable on AB, and f of x less or equal than g of x for all x in AB, then integral f of x dx less or equal integral g of x dx. The last property, not the last, sorry, additivity. Additivity. If, not if, f is integrable on AB, if and only if for arbitrary c between A and B, f is integrable on AC and CB. Moreover, integral from A to B f of x dx equals to integral from A to C f of x dx plus integral from C to B f of x dx. So if you have interval AB and you have a point inside, then integral of a whole interval equals to the sum of two integrals over each part. And the last property is an estimate. No, maybe I'll give it later. for this theorem it's enough. So, proof. Now it is essentially easier to use Riemann definition for the first, right? So look, what we should do. We take arbitrary integral sum f p psi I. Psi, we wrote just psi, right? As f p psi equals to sum f of psi I delta xi. So we know this tends to the integral as the norm of partition tends to 0. And analogously, we can say about integral sums for the function g. Then, what is about integral sums for the sum f plus g p psi? They are just sums f of psi I plus g of psi I delta xi, and they are just sums of integral sums. So it is obviously from definition of such a limit that it tends to the integral to something, right? To something. It tends to something, and if it tends to something, then this is integrable, and the integral is precisely the limit. So it follows that the integral equals to the sum of those two integrals. Second property is quite analogous, the same, just multiply by a constant c, nothing else. Now, third property. What we should do? Look, we third property. Firstly, suppose f of x greater or equal than 0 for all x in AB. Then, what can we say about integral sums? Look at them. All values are non-negative, right? Here we have delta xi, which are also non-negative, lengths of small intervals, so it is less or equal to 0, right? All of them. Hence, their limit, we know it tends to the integral, right? And it follows that this limit is also non-negative, right? The limit of non-negative things is non-negative. And then now, for arbitrary case, what can we say? F of x less or equal to g of x, then g of x minus f of x non-negative, right? And we know from the first and second properties, integral of difference equals to difference of integrals. Hence, it is non-negative, and that's all. Now, fourth property, additivity. Here, what we have? Look, here it is better to use Darboux definition. So, f is integrable if and only if you can find a partition P of your interval such that you have this inequality, right? Now look, if we have interval AB, right, and we have a partition such that this difference is less than epsilon, I mean if the function is integrable over interval AB, then what can we do? Take arbitrary C. Then add this point to the partition. So P star, let it be P together with the point C. So we add the point. Then, as we know from properties of Darboux sums, we know that upper sum will be small in general, right? Lower sum will be great. Hence, the difference will be smaller. So, U of P star, F minus L of P star, F is less than epsilon. Hence, what we obtain? What is P star? P star consists of two partitions, in fact. P star can be represented as a partition P1. Here we have partition P1 of the interval AC, right? And a partition P2 of the interval CB. And this is precisely the sum P1F minus L of P1F plus P2F minus L of P2F. That is sum, right? So, if the sum of two non-negative terms is less than epsilon, then each of terms is also less than epsilon. And it means the function is integrable over every of intervals AC and CB. What's about equality for integrals? We know that the integral is in between, somewhere in between, right? The integral over AC is somewhere between those, integral over CB somewhere between those. And here we have sum. So both integral over AB and the sum of integrals are somewhere in this interval between lower and upper sum. So both numbers are inside the same interval of the length epsilon, where epsilon is arbitrarily small. Hence, they coincide. And the last thing here, converse assertion. So if the function is integrable over both AC and CB, then what happens? We can find P1 and P2 such that this is small, and that, right? And then we consider partition which is union of those two, and for that partition we have, okay, with 2 epsilon, right? If we choose here with epsilon both, then for the sum we'll obtain 2 epsilon. Once again, we deduce that if the function is integrable over each of those intervals AC and CB, it will be integrable over AB. That's all.